In all of our examples so far, we have looked at exponential functions that are growing. Let's look at some examples that involve exponential decay. Recall that an exponential function is of the form p of t equals p naught times a to the t, where a equals 1 plus r, and r can be calculated as the relative change over 1 unit. If a is greater than 1, then there is exponential growth. This is useful for modeling populations, loans, amongst other examples. If a is less than 1, then there is exponential decay. Let's look at some examples of this. In our first example, let's look at caffeine in the bloodstream. The amount of caffeine in the average person's bloodstream decreases by 11% each hour. If someone drinks a coffee with 120 milligrams of caffeine, how much caffeine will be in their bloodstream 6 hours later? To solve this, we'll use the model p of t equals p naught times a to the t, where p naught is the original amount of caffeine, which is 120. A is given by 1 plus r, where r is negative 11%, because we're decreasing by 11%. So a equals 0.89. Another way of thinking about this is after 1 hour, only 89% remains. So our model is given by p of t equals 120 times 0.89 t, where p of t equals the number of milligrams of caffeine after t hours. The question, how much caffeine will be in their bloodstream 6 hours later, is asking, what's p of 6? Using our model, we can solve p of 6 equals 120 times 0.89 to the 6. Evaluating, we get roughly 59.6. So after 6 hours, there is roughly 59.6 milligrams of caffeine left. Now let's look at another example. Radioactive elements decay exponentially as well. In particular, the radioactive element cobalt-60 loses 13.5% of its mass each year. If we have a sample of cobalt-60 that has a mass of 250 grams, how much will be left after 2 years? To find the solution, we need the model p of t equals p naught times a to the t, where p naught is 250 and a is 1 plus r, where r is negative 13.5%, because we lose 13.5% each year. So a equals 0.865. Again, a equals 0.865 also represents the fact that after each year, only 86.5% remains. So our model is p of t equals 250 times 0.865t, where p of t equals the number of milligrams of caffeine after t hours. Here, the phrase, how much will be left after 2 years, is asking, what's p of 2? Evaluating our model, we get that p of 2 equals 250 times 0.865 squared, which comes to roughly 187. So after 2 years, there will be 187 grams of cobalt-60 left. So in this example where we started with 250 grams of cobalt-60, and after 2 years there was only 187 grams of cobalt-60 left, what happened to the rest? The other 63 grams of cobalt-60 decayed into nickel-60, with possibly different mass. A chemist would ask, what happened to the rest? The other 63 grams of cobalt-60 decayed into nickel-60, with a possibly different mass. Note that the decay of cobalt-60 into nickel-60 is not part of our course, but an interesting piece of information.